We've been talking about gases and their behavior, and previously we talked about chemical reactions, and now we're going to bring those two ideas together. Some reactions involve reactants or products in the gas state, and so now that we've learned how to do gas law calculations, we can calculate the amount of gas that's present in these reactions. The amount of gas is often specified in terms of its volume at a given temperature and pressure. And so what we can do is we can use the ideal gas law to convert that information to moles. And moles is what we needed, wasn't it, when we did the stoichiometry. Grams to moles to grams was stoichiometry. Do you remember that? Say yes. Yes. Thank you. So grams to moles to grams. Well, sometimes this part in the middle is the part that's always the same. Sometimes the beginning or the end gets changed. So if we have a pressure, a volume, and a temperature for a gas, bless you, we can use that to calculate the number of moles of the gas, and then proceed and find the moles of the other substance and perhaps the grams of the other substance. Or sometimes we'll start with the mass and go to moles, and then we want to know the volume of a gas at a particular temperature and pressure, and so we can also tweak the ending. So that's the big idea. We're building on stoichiometry, just using our knowledge of the ideal gas law, which enables us to calculate the number of moles of a gas based on its pressure, volume, and temperature. So here's a reaction in which 4.58 liters of oxygen were formed at 745 millimeters of mercury and 308 Kelvin. How many grams of silver 1 oxide decomposed? Well, let's treat this as stoichiometry because this is a stoichiometry problem. So we've got a volume of oxygen. So let's write this volume under oxygen. So 4.58 liters of oxygen. And then we've got a pressure and a temperature. We could write those down there also. There's no harm in that. And then here's the question. How many grams of Ag2O? So question mark, grams. Use the equation to organize your information. All the stuff pertaining to the oxygen, right under the formula for oxygen. The question, how many grams of this? So then, this is looking like stoichiometry, and so we say grams to moles to grams. And here at the end, it is asking us for grams. But are they giving us a mass for what we're starting with? No, they're not. So we just need to change this first step. Here we've got pressure, volume, and temperature of a gas. And we're going to use that information to calculate the moles of the gas. So to do that, we need to use the ideal gas law. So this is our volume, this is our pressure, and this is our temperature. PV equals nRT. What are we trying to find? N. We need the number of moles. So we're going to rearrange this equation. We want to get rid of R and T from that side. And if we divide by RT on one side, we have to divide by RT on the other side. And so we have N equals PV over RT. Are these units going to work? All but one. What about the pressure? Yeah, we need to make that into atmospheres. So 745 divided by 760. 0.980 atmospheres. Whenever we use the ideal gas law, we're keeping in mind the units of the ideal gas constant. I'm going to write it here at the top. R equals 0. I don't know why it flew up like that. 821 liter atmospheres per mole Kelvin. The units on this constant tell us what the units on our other quantities have to be. So that's why we changed the pressure. The temperature was already in kelvins. The volume is in liters. So then we're going to put this in here. 0.980 atmospheres. And the volume is 4.58 liters. And R is always the same. It's always nice when there's some constants in life. And 308 Kelvin. Just be careful that you don't miscommunicate with your calculator there. Times 4.58 divided by 0.0821 divided by 308. That's moles of oxygen. We took the volume, the pressure, the temperature of the oxygen, and we calculated N. These units all cancel out, and we're left with moles. But we're not done, are we? What we did is we went from PVT to moles. Now what do we need to do? We need to go to moles of Ag2O and then to grams. We need some space. I can't turn the page, so I'm just making some room. So 0.177. I'm just thinking I'm going to round that 4 up to a 5 and just bring that along for the ride. O2. What do I want in the numerator here? I'm looking at this part. Moles of Ag2O. This O is too small. And then what goes on the bottom? Moles of O2. See, then those units cancel out. And here's my path that I left up here. Moles of O2 to moles of Ag2O to grams. So over here, this is grams of Ag2O. And then what goes in the bottom? Moles of Ag2O. What goes in this spot right here? A 2. Because we look at the equation, this is where we get our mole ratios. 2 moles of Ag2O will make 1 mole of oxygen. So it's 2 moles of Ag2O for every 1 mole of oxygen. How do we find the number that goes over here? We need the periodic table. So we've got silver is 107.9. 107.9, and there's 2 of them, so times 2, and 1 oxygen at 16. And so the molar mass of Ag2O is 231.8 grams per 1 mole. So 0.1775 times 2 divided by 1 times 231.8. I'm going to round this to 3 sig figs because that's what all my numbers had to start with. So 82.3. So we took what we learned about stoichiometry, where we learned how to calculate grams to moles to moles to grams, but also sometimes we just went moles to moles, or grams to moles, or moles to grams, right? And now we're just adding a little twist. For this time it was at the beginning. Sometimes it can show up at the end. We can use the ideal gas law to calculate moles of a gas. Any questions? Here's the STP business that we needed for the lab, but we didn't quite cover in time. Standard temperature and pressure. So standard temperature and pressure, and that gets abbreviated STP for standard temperature and pressure, not a brand of motor oil. Standard temperature is 0 degrees Celsius, which is the same as 273 Kelvin. Standard pressure is 1 atmosphere. I've never researched this, but I'm pretty certain that the reason this was chosen as standard is because it's very easy to establish these conditions. 0 degrees Celsius is the temperature of an ice bath, an ice water bath. So if you put your gas container inside of an ice water bath, even without any equipment of any sort, you can be pretty certain that the temperature is at least very close to 0 degrees Celsius. It's easy to do. 1 atmosphere, that's standard atmospheric pressure. So if your container is open or equal in pressure to the outside, then you can be certain that the pressure inside is 1 atmosphere. That helps me to remember what STP is. It's easy. Ice water, it's easy. Now, to establish something that's at 25 degrees Celsius, you're going to need a thermometer, and you might need a way to heat something up or cool something down. That's going to be more complicated. Sticking something in a cooler full of ice water is easy, doesn't require any special stuff. Okay, having it exposed, equal in pressure to the atmosphere. That's what we did when we did our lab. Is we just adjusted the levels of the liquid inside and outside, and then we know the pressure inside is equal to the pressure outside. Now, is the pressure outside always exactly 1 atmosphere? No, but it's pretty close. It varies a little bit. Atmospheric pressure varies only a small amount. It doesn't go like between 1 atmosphere and 2 atmospheres. We would be very uncomfortable if the pressure was 2 atmospheres. So then we can do things like calculate the volume of 1 mole of gas at STP. So this ends up kind of being shorthand. So at STP, is telling us what the temperature and the pressure are, right? The temperature is 0 or 273, and the pressure is 1 atmosphere. So calculate the volume of 1 mole of gas. Calculate V, N is 1, and temperature and pressure are given. What equation are we going to use here? Pivnert, ideal gas law. So PV equals nRT. And we're going to rearrange this for volume, right? So we need to get rid of the P. And we'll divide both sides. Now we've got volume equals N, it's a bad N, R, T over P. What's N? 1 mole. That was given to us in the problem. Calculate the volume of 1 mole. What's R? 0.0821. And what are the units? Liter atmospheres per mole Kelvin. And what's the temperature? 273 Kelvin. Standard pressure and temperature. 273 Kelvin. And we're dividing by the pressure. What's the pressure? 1 atmosphere. And so our units are going to work out. Check me by doing that on your calculator. Comes out right, huh? This is the volume of 1 mole of any gas at STP. You can't do stuff like that with solids and liquids because the sizes of the particles matter. Kinetic molecular theory of gases tells us that the size of the volume of the actual gas molecules doesn't matter because they are so small compared to the big spaces between them. It's like the people in Wyoming. Why do I get those mixed up? If they're all really, really fat or really, really skinny, does it really matter in terms of how much space they have in that whole state? Did I tell you guys about Wyoming? I did, okay. Now, when people are in an elevator, in a confined small space where the size of the people is significant relative to the size of the space they're occupying, then it matters. But if you're talking about 400,000 people in a large state, the size of the individual people doesn't matter. In a gas, the size of the particles doesn't matter. And so a mole of hydrogen, little teeny tiny molecules, is going to occupy the same volume under the same conditions as something like xenon. Xenon is a gas. Each atom of xenon weighs 131 grams. It's a lot bigger than a hydrogen molecule that only weighs 2 grams. But a mole of xenon occupies 22.4 liters at STP. So this guy right here, 22.4 liters per mole, this is the molar volume of an ideal gas at STP. And this ends up being a very convenient conversion factor. 22.4 liters per mole. So we talked about molar mass was the mass of 1 mole, right? Molar volume is the volume of 1 mole. So this is a number worth remembering, 22.4 liters per mole. And I should have gone to this when I was talking about the people. Oh, wow, that's xenon. Xenon and helium instead of xenon and hydrogen. Good grief. Okay, so here's helium. Here we have 1 mole representation of 1 mole of helium in STP. its volume is 22.4 liters. The mass of it is 4 grams. Over here, we have a mole of xenon. The individual gas atoms are larger, but the gas still occupies a volume of 22.4 liters. Does it weigh more? Yeah, it weighs a lot more, 131 grams instead of 4 grams. But it still occupies the same volume because it's a gas. 1 mole of any gas at STP is 22.4 liters. So we can use this as a shortcut. How many liters of oxygen at STP are required to form 10.5 grams of H2O? And here we have our balanced chemical equation. So this ends up being stoichiometry with a gas twist to it. So 10.5 grams, well, let's write that under H2O. 10.5 grams of water. Question is, how many liters of oxygen? The question mark, liters. They're not specifically saying the temperature is this, the pressure is this. They're just saying at STP. At STP. That does tell us the temperature and pressure, though. So stoichiometry, our little mantra was grams to moles to grams. We have to start with the thing that we have a number for. So this time we are starting with grams, aren't we? So we're going to start with grams of water and go to moles of water to moles of hydrogen. But then instead of going to grams, we're going to go to liters at STP. So what we'll do is we'll use stoichiometry to calculate the moles. Okay, stop me when I do stuff like this. What's wrong with this picture? It should be under oxygen. I'll blame that on being sick. I take any excuse I can get. We'll take our mass of water, grams of water to moles of oxygen, and then to get to liters, we're going to use Pivnert, the ideal gas law. (10.5 grams of H2O. What's next here? On top, moles of H2O. And what do we want on the bottom? Grams of H2O. So those guys cancel. We're going moles of water to what? Moles of oxygen. And what goes on the bottom? Moles of H2O. You starting to get the hang of this now? So that gives us moles of oxygen. We can't really just throw the other stuff in here. So what we're going to do is we're going to stop here and calculate the moles of oxygen so that we can use that in the ideal gas equation. So this guy's our mole ratio, right? We get the numbers in front of moles of oxygen and moles of water from our equation. 1 mole of oxygen for every 2 moles of water. 1 mole of oxygen for 2 moles of water. And then this is the molar mass of water, which would be 2 times the mass of hydrogen plus the mass of oxygen. And we calculate this. 10.5 divided by 18.02 divided by 2. 0.29134. There's some other digits. How many sig figs should that number have? 3. I'm just going to underline the 1. I'm going to carry along those next 2 guys, just so I don't end up with rounding errors, because this is not my final answer. It's best not to round until you get to your final answer. So that's moles of oxygen. This is equal to N in PivNerd, right? So we had PV equals nRT. And what are we trying to find? Volume. Trying to find volume. So we need to rearrange this and get volume by itself. We'll divide by P on both sides. So the volume will equal nRT over P. We just calculated N, 0.29134 moles. We've got R. What's the temperature? 273. Because that's 0 degrees or 273, 0 degrees Celsius, 273 Kelvin is standard temperature. What's the pressure? 1 atmosphere. So we've got the 0.29134 times 0.08. Oh, stupid. Okay, we're doing it the hard way. Duh. Sorry. I'll show you the easy way in a minute. This can work too. This is fine. It's fine. It's absolutely fine. We just use this molar mass conversion factor. So this is what you do if you forget about the molar mass of a gas at STP. So we got our answer, 6.53. My head is seriously very foggy. It's the Mucinex DM. So, what would be easier? That's easier, huh? Oh, I can't even enter things in my calculator today. 0.29134. Look at that. We came up with the same answer. Except I can't even... Good. The good news is that this medicine is the 12-hour kind. So I'm going to be spacey all day long. There we go. Any questions? That is finally the end of the chapter.